Okay, guys, so this is Robotics and Artificial Intelligence Meetup number 47. As we know, the theme for this month is humanoid robots. And last time we did reverse engineering of Atlas from Boston Dynamics, but we covered how it performs, let's say, these complicated parkour operations. And today we'll be focusing on the dance, the algorithms behind the dance performance that we see in these popular Boston Dynamics videos, right? So today we'll be keeping the session a bit short because we already covered a lot of the things in the last session. And it will be a continuation of the previous session, but if you didn't attend the last session, things should still make sense because I'll cover the necessary portions from last session again. So talking about our community, we focus on actively learning robotics and artificial intelligence by taking up several case studies, and there are a few roles that you can fill if you want to present your idea or your project in our meetups. Feel free to do that. You can just check the meetup volunteer channel and write details about your project, or if you want to present your research paper and have a discussion about that, that is also possible. Just take the paper reading volunteer session, and these meetups will be recorded and shared online. So if anyone has any trouble, you can just reach out to me and I'll edit out the portion. Yeah, these are some more roles that you can check in the assigned roles channel on the server. So let's start already. Oh, wait a minute. I think this is. Yeah. Okay. Yeah, I deleted the parkour stuff, but I just wanted to keep the main slide. So, yeah, talking about Atlas. So, just a very brief point that we also covered last time. So, the Boston Dynamics has this robot lineup, and the most popular one spot that we see is a more general purpose robot, and there are also more specific robots which perform specific operations in industry, for example handle and pick. And with Atlas, the primary focus is not to deploy it in any industry. For now it is basically focused on pushing the research boundaries in robotics, and that is why it is made to perform these hard complicated problems in robotics. So the focus of Atlas robots is purely R&D, and it says that it's the most dynamic humanoid robot. I'll just not talk too much details about Atlas in general, as we talked about it last time. So Atlas is known to perform parkour and dance. So we talked about parkour last time, but why do we need to why did they target parkour and dance movements rather than having a predefined set of standard tests for these robots? And the reason for this is because both of these operations require the need of rapid behavior authoring, which means that the behaviors need to be generated very quickly, and also in a way this tests the boundaries in research, and it requires whole body control of the robot. So mainly the idea is because of the complexity of the problems involved, parkour and dance are targeted. So last time we saw about parkour. I'll also tell briefly about this because this is also a part of the dance system that they are using. So what they're doing is basically they are using trajectory optimization to first generate a database of several behaviors. So for example, this behavior is 360-degree rotation, this is jumping, and these are other behaviors. And what happens is that once this database of behaviors is generated offline, and we have a library of these template behaviors, and then an online planning control system looks at the environment using the perception system. So this is being done online, and this combined with our library of template behaviors actually is fed to a model predictive controller. such that one behavior is selected from the template behaviors and then adapted to the perception system. So an example that we talked about last time was, for example, if the robot has to jump on the top of a box, but the boxes could be of different sizes, right? So of course the template behavior that it would select is that of jumping, but the trajectory end point and starting point would be different depending on the box size that it perceives in real time. And this means that a combination of real time perception and template behaviors is used to modify the trajectory, and these are then fed to the model predictive controller, which executes it in real time. So this was the idea that we saw last time, and also little bit details about uh, offline and online optimization approaches. So we saw that here in this case the robot is simply represented by an ellipsoid, and we saw that this the size of the ellipsoid actually represents the inertia of the robot, and we are talking about jumping operation. So the robot would jump and then lie flat on the surface. And so first of all, momentum dynamics or dynamic optimization is performed, and that means representing it in the form of an ellipsoid. And then after that, full body kinematic trajectory is generated that is consistent with the centroidal solution. So this is after this we get the trajectory, and then the trajectory is optimized, and this is then the same thing that we saw in last slide. So the offline optimization process generates the set of template behaviors, and an online model predictive control system then uses the template behaviors plus the perception model to generate the real time trajectories, so to say. So this is what we saw last time, and now we can focus on how all of these things actually fit with the dance system. So most of the slides today are taken from this webinar by Scott Kunder Zima. I don't know how to pronounce his last name, but from his slide, he's the head of Atlas division basically at Boston Dynamics, and he has explained it in a lot of detail. So if you want to also watch it at a later time, I could link to the couple of webinars that Boston Dynamics has in this area, and I think that would be very helpful.
Yeah.
Sorry.
Yes, please share that webinar.
I'll definitely share that, and I think it's not very popularly known that this much detail is already being shared on YouTube. So I'll definitely share that. So this one here, so one of the ways to capture the motion and actually to train the robot to perform the motion is to capture the motion by an animation system, right? So using an animation software, all of these motions are basically generated and then applied to a real robot. And then of course physics based specifications are done, and all of these things are applied to the real robot. So one of the main parts is modeling mechanical compliance. So you can imagine like dance movement is pretty complicated, right? So it requires the robot to touch the ground and then perform rotations of feet and apply forces in different at different angles of different magnitudes and so on. And so robot and ground compliance is very important in this case. And unmodeled, this impacted state estimation and leads to recovery motions. So this is also, I have not linked the video, but this is, you can see the video in the webinar, and basically it shows here how it recovers from, let's say, slipping of feet position, so that the dance movements, the dance behaviors are more let's say smooth and follow one step after another in a more in a sequentially correct way. So this is where everything comes into picture. So we saw the model predictive controller, the online optimization method, and then trajectory optimization offline method, which gives us a feasible trajectory, and then this is fed to the robot. Right, so this is exactly the same as we use for parkour, and that is why we don't need to talk again about this. Uh, this portion is exactly the same as parkour, but the only difference here is that as we saw here, we the animation videos are actually generated by an animator, and then a dance expert actually generates the movements in real time, and you can see that these are then fed to the animator. So this is sort of utilizing an animation system as well as a real dance expert. So a combination of these to refine these dance movements, and these then generate the kinematic trajectories, and rest we know the process. So this is the Atlas dance approach, and this is again the optimization approach that we saw, and the same approach is basically used. So yeah, you don't need to repeat it. So here we see an actual choreographer providing these dance movement sequences, and the animator then takes these sequences and then makes a proper, smooth transitions on a simulated robot. Uh,
I think for this one transfer of animation, there is this one paper which named as Anybody Can Dance.
Anybody can dance. Okay.
Yes, yes. In on YouTube, you can search this as Anybody Can Dance. By, I think it's by Harvard. So idea is what they have done. You take a video of any action done by some professional, whether it's a video clip of LeBron doing some basketball moves or some great dancer,
Yeah.
anything, and then you apply that same transfer to the person standing in the room, and you can see the body moving. That kind of a transfer. That paper is available.
I
So
think
it's
I
doing
think
something
I've
same.
seen it. I think I know which one you're talking about.
Yeah.
But I think like aren't they that I think that is a different thing, right? They are using probably pose estimation and then transferring
Yeah,
to.
it's a pose estimation and a GAN based approach.
Yeah. So that's a different approach actually. So here it's more simpler. So they would have,
Okay.
like, let's say these tracking the suit that they wear to track these movements, right?
Okay, okay, okay,
Yeah, and then these this data is then used and then applied on an animator. So animator
okay,
filled in important details, stylized transitions between dance movements, trade-offs to cope with robot ROM, musical
okay.
arrangement
Something
experiment.
that is used
Yeah.
in film industry.
Yeah,
Okay,
yeah. So this is like, yeah, no, they're not using any computer vision or anything for that. This is more,
okay,
like
okay.
as they use in films, for example. So here we see how model predictive control is being used, and this is again like the same thing is explained in a bit more detail. So we take this centroid model predictive control and kinematic optimization, and this gives us the wrenches and the forces and desired acceleration, and then inverse dynamics is performed, and then we get the torque. So here basically we have some variables like the wrenches, center of mass, uh, linear angular momentum, angular excursion, and contact positions, and the cost is track reference. uh, yeah, so the movement of the robot, and then we linearize and solve at every control tick, exploit problem structure for speed, solve kinematic optimization to derive consistent touchdown configurations. Yeah, to be honest, this is the portion, a part of the portion is similar to this, but yeah, I don't remember the details of it. I think we can watch
It's
the
the idea of basically your movement transition, especially when you are taking sort of jumps and actions which need, speedy transition, like
transition between
in,
dance steps.
yeah,
Yeah,
speedy
yeah.
moves. So for that, this kind of arrangement they have, like prepare a track, optimize it, and find the final position. That kind of approach.
Yeah, so basically, there's a lot of math underlying it to calculate the
Yes,
inverse
yes.
dynamics and all. I think yeah, this for that I guess in the webinar also they have not explained it in too much detail, but for that you have to read research paper and so on, you know. But yeah, we are just taking a general idea about this thing. And here is here is another thing of how we can author multiple pathways. So yeah, there's a couple of things. As they mentioned in the webinar, like some of the movements that the robot that the animator performs can be directly transferred to the model predictive controller, whereas some of the movements require some refinement, right? So in reality, some things just work from the animator when plugged directly into model predictive controller. So this is uh, let's say directly from the animator after some contact segmentation, whereas others require trajectory optimization. So this one either as a cleanup step or the source of the behavior, and the final dance routine was a concatenation of behaviors. So this is what we also talked about here, right? The movement of the transition from different movements, and this is how they define different routines. So let's say this is one routine where it's actually fed directly from the animator, and then this one where you have to where trajectory is optimized, and then here directly again from the animator, and here uh, again trajectory optimization and so on. So these are different sequences uh, that they combine to form a routine. And here we have offline optimization and performance limit, optimized arc jogging, motion rides.
Onboard computing.
Sorry.
You can say this as onboard computing, I guess. And
Uh, yeah, I mean, yeah, both of these offline and online optimizations are on board, and yeah, exactly. So optimized arc jogging, motion rides, torque limits, animation exceeds them, whole body coordinated spin jump, easier to get right with optimization. But basically, this is the same thing but applied to dance with that we talked about offline optimization, right? So here are two movements. So here this one performs a ballet kick, and I mean, of course, these are more fun to watch the videos, but I just took
yeah,
screenshots. Yeah, yeah, that that is the thing. Um, Quasi-statically stable, low joint velocities focuses on the style of arm or leg movement. Yeah, of course. I mean, this is nothing too technical here. They're just showing what kind of movements that they programmed it, right? And this one again, not no complicated rotational or inertial changes, well within robot torque limits. Yeah, maybe I'll open the webinar for videos if you have time. And here, yeah. Uh, so they also take a feedback of the behavior timings basically, because model predictive control needs to adjust the behavior online. Uh, yeah, here they show that the error difference if we don't take any feedback, and then if we take a feedback, then the error is then eliminated. Normally this is used to maintain balance, adjust touchdown timing, etc. For dance motions we can use it to track a desired bpm and align to music. uh, beats per minute. Yeah. Yeah, basically this is another feature that they have, that they're taking feedback in real time and adjusting the behavior online. And here, this is how they represent the forces, right? So this is 1
4 feet, I
feet.
think.
Yeah, this is exactly, this is 1 feet, and then at the corners of the feet, they have this force model. Point force representations can overestimate feasible yaw torques, leading to foot slip. Different approaches to representing contact wrenches offer different trade-offs in terms of variable coupling or sparsity, problem size, ability to independently control and contact path size, and force limits.
It's like a standard problem when it comes to providing a confidence value. Whenever you give a points point based confidence value, it tends to overestimate. But if you,
Yeah.
instead of that, you provide a range of confidence, then it becomes much easier to get a more accurate result. So if you'll see the 2 points that they have, two examples, that force example that they have shared, one is with a single point and another with four different points.
Yeah. But the one where we have the contact, we have the forces at four endpoints. I think the idea is
Yeah.
that you can independently control the contact path size, right?
Yes, yes. And in fact, if we'll see, the four contact points are much more close to reality compared to 1 point, because on a on a point based sample, it's hard to say that all the dynamics will be very much accurate, because things like momentum and all will also play the picture, right?
Yeah, 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 yeah. Exactly, and that is also the point that they laid in this slide, basically, that point force representations also tend to overestimate the torques, and leading to foot slip, right? This
Yes,
is
yes,
what
yes.
we talked about. Yeah. Oh, and that's it. Actually, that's it. Yeah, I thought we had more slides, but we can watch the, let's say, webinar I'm talking about, right?
Yeah, sure.
um, so there are a couple of things. I think this one is the one where he talks about parkour. Robotics today, recent progresses on Atlas.
Okay.
This is containing most of the technical details we know, and this one is, if I remember correctly, yeah, robot dancing using optimal control. You see, here they have the movement, so it's more fun to watch, right?
Yeah. Actually, I think I have seen these videos, independent videos, I have seen.
You mean like the clips of this, right? Or not the
Yes, yes,
webinar?
yes, yes. Not the webinar, the clips.
Yeah, it has just like 1700 views, right?
Mhm.
So here, let me actually let's do one thing. Let me share the let me stream the audio as well, so you can hear it.
Sure.
Let me know if the audio is uh, clear. Is it? Can you hear the audio?
Yes, yes.
Yes, yes.
Okay, okay, perfect. Yeah, so I mean, let's talk about let's hear from uh, this one is what we were discussing, right? So of course I'm not fully prepared for this because yeah, I mismanaged my time, so I didn't get the time to. I had to rewatch this to explain things better, but here we have it. So here we go.
Another little detail that I thought was a little bit interesting was us thinking about how contact force representations can sort of matter in practice when doing a lot of motions that involve single stances and lots of body twisting and things that would, on the face require lots of yaw torque on the feet. And so the observation here is that if you represent something like the foot as a set of point contacts, maybe at the corners of the feet, and then apply linear friction constraints to those things, that works pretty well, as we all know. It's a pretty standard thing to do, but it also is not really representative of what's physically happening on the robot, right? So the robot's actual foot is a surface interacting with another surface, in our case, a client surface. And so the effective pressure distribution on the bottom of the foot doesn't really coincide with this notion of having, four pure point forces at the corners. So in some cases, you could have the issue of overestimating the available yaw torque before breaking stiction. And also writing things down this way sort of implies a sort of coupling between what your contact patch size is, what your friction limits are, and how much yaw torque you have available. So one of the things we felt like it was worthwhile to do is rethink what are the different options for parameterizing, wrenches being applied to bodies in the robot, so that we could apply specific constraints to, variables that we think mattered, like yaw torque limits. And so this is work that we were inspired by, reading papers like Roan and all. And I think there's several good choices here, but this is something that we ended up rethinking, making some changes to make GANs a little bit more reliable.
Yeah. So here he also talks about that how representing it using point forces is not the best way, because it's the robot feet is a surface, and it makes a surface contact, right? And also the good part about this webinar is they've also linked papers and all, so if anyone wants to read these in more details, basically.
Yeah.
So
And just one thing I would like to add is this point estimation and range based estimation. This is basically a statistics problem. If you try to read anything that goes into confidence interval, if you read this segment of statistics, you will be able to understand this much clearly.
mhm.
The confidence interval, basically it's the branch of statistics which actually points out this very thing, like that standard method of like saying you want to estimate something, so either you can give a point estimate or a range of confidence where possible solution can be, and how better the performance goes. So that kind of a theory is there in confidence interval. So that's something interesting if you are if you would like to know more about this
So it's confidence interval is
interval. Yes,
what you're saying, right?
yes.
Is there any specific resource, or just
No,
general?
it's a standard term in statistics.
Mhm. Yeah, I mean, it's a range of values we are fairly sure, or true. Okay, true values lies in. Um, Not sure if this is actually linked with this, because here it's about having, let's say, the distributed forces rather than point forces, right?
Exactly. And
Yeah.
how do you estimate that how many forces are required to give a perfect representation? So I,
Mm-hmm,
in
mm-hmm.
ideal world, yes, you give one point, point of estimation where everything works perfectly. But in real world example, that tends to, as he says, you overestimate the yaws and things
Yeah.
like that, which leads to foot slip, right? So you need to find out how many forces you can actually use that can, it's not a overestimation but also not a underestimation.
Mm-hmm, mm-hmm.
But from where are you gonna get the feedback then? This is the question. The feedback you get from sensoric under the foot or how?
Sorry, I'm sorry. Can you please say again?
The feedback from where he is getting the feedback exactly.
Feedback for?
Yeah,
Feedback from
they actually have pressure sensitive feet. So there's sensors on the feet that you. This is what you mean, right? How is it getting the forces?
yeah, is it strain gauges or what exactly? What how they are getting the feedback then, and the
Um,
feedback how they are using it.
I think it's just they just mentioned pressure sensitive feet. So wait a minute. Let me open the other. Let's say in the other video. I think I'm not sure if here also they have mentioned about hardware. Yeah, let me open the previous slide quickly.
Because even with the feedback from the sensoric, they need to calculate every time the center of gravity, right? Because it's changing.
Uh, I think when they use this template method, do you think that at that point of time they might be having a range of possibilities? Because then they already have this centroid based approach to calculate the entire inertia of the robot, right?
So here you see, if you can see my screen, they have just mentioned, and this is also from one of the official presentations. So, force sensing feet is what they are labeling it as. I don't know if they're using strain gauges or some other sort of arrangement, basically.
Uh, yeah, I get the idea, but that while moving, you're changing the center of gravity. So the center of
Yeah,
gravity need to be calculated every time. So through this force, they need always to calculate the center of gravity because it's moving, and then it take it to the feedback while they are moving, right? This should be always because, for example, in human, the brain will calculate always the center of gravity. With that, you're gonna get the feedback or reaction. So
yeah,
while he's
yeah,
tapping is moving, so there is some kind of technique which they are reading.
yeah. There
I
must
think it's
be, there must be. That makes sense. But yeah, officially, I couldn't find much details about this thing. Like, what exactly are they doing about it? Yeah. Okay, let's go back to the webinar again. So here we saw this, and then let me see some of the things that we wanted to see videos of, right, in the slide. Let me see. Okay, yeah, let's see this.
moving the arms and legs around. That works really well without much trouble. Things like the mashed potato may be visually a little bit more surprising, right? So here, this is a pretty non-trivial motion that has some lots of different contact changes, flight phases, body motion in flight, things like that. And so I think this is pretty amazing that the MPC controller is able to take something that's a purely kinematic reference of this motion and then online turn it into something that is incredibly reliable on the robot. So what are some of the technical things that we ended up doing that were slight extensions of what we had before that specifically addressed some issues that came up with dance? So one thing is, since the MPC controller is able to adjust timing of behavior, which it normally would do in the context of locomotion to, extend the stance time of a particular maneuver to maintain balance, or maybe to adjust the touchdown time if it maybe jumped off a box of a slightly different height than it expected, or if the momentum at liftoff was slightly wrong. These are all really important things. But in dance, timing is really part of the behavior spec, and it's really important that you try to stick to it. So having explicit feedback on a reference timing was pretty important. And once you have that, then you can take a single dance input trajectory and repurpose it for a range of beat frequencies for different songs. So we're able to take, pretty much any of our dance moves and scale them up and down within reason to match different song frequencies, sort of as we wish.
Yeah.
Another
Yeah, so the reason why I had so few slides in the PPT is because after that it's just uh, fun demonstrations that they have had in the webinar. After that they didn't really have any much technical details there. But yeah, let's
large
see
fish
here.
forces during those big
By the way, just to confirm, you can also hear the audio, right?
Yes.
Okay.
configuration changes was we realized there were some compliances in that robot, and of course known compliances with the robot and the MMA mats it usually operates on that could excite some bad dynamics in our state estimation. So here's an example where we are doing a part of the routine where these compliances were not appropriately modeled. And so what you can see is the robot kind of loses it and does some recovery behavior. Now, of course, as a roboticist looking at that, that's pretty cool, right? Awesome recovery. But dance is a little bit of an exercise in nailing it, right? You can't be doing step recoveries and all these wild things during the dance move. You kind of lose it. So appropriately modeling all these important physical effects actually ended up being really key to getting these moves to look convincing and be reliable and very similar from run to run. All right. Now let me tell you a little bit about the sort of process for actually putting this together as a production. So the engineering team really didn't start working on this until last year, but far before that, back in the 2019, Mark Raybert had been working with Monica Thomas, coming up with a concept for what it would look like to have, a couple atlases and a spot and a handle all dancing together. And so I think what's amazing to look at with this video is how close this early concept without any context for what the strengths and limitations are of the robots is to what we actually ended up doing, for the final thing. So this is cool. I mean, it's fantastic to see something like this, a high-level vision, which gave us a sort of lighthouse to work towards, taking this, breaking it down into smaller pieces, doing, a little bit of iteration, based on our understanding of feasibility and so on, and what we see experimentally. But this was just, a total key to success is having this kind of top-down vision for putting together something like this. So really most of the frequent robot testing for this started to happen in the later half of 2020, which was of course during the pandemic. So we had a skeleton crew of Atlas engineers who would go in just to run experiments, including Jared DiCarlo and Robin Dietz. And so there's a lot of these kind of things where, just a couple people in the building and trying to figure out, what moves worked, what didn't work, getting things that kind of looked okay, kind of weren't super reliable yet. But I think what we usually found is when we start off with a new behavior, we run it on the robot. A lot of the time we were sort of 70% of the way towards something that we would call complete. And then there was a bit of refining over a couple iterations to get something that was really reliable. Here's an example of running our first robot synchronization test. So here's some network communication that's happening that's triggering behaviors on multiple robots. They're just doing some of the standard 180 jumps, and then they'll execute the same dance routine together. And so the question here was, can we start them together with a reasonable precision, and with the open loop time tracking happening on both robots be enough to keep them in sync together? And the answer is basically yes. So we didn't have to do any timing feedback across robots in order to make this happen. Each robot was independently good enough at tracking its own time. Now, of course, Atlas wasn't the only star of the show. We had a couple other robots involved here, and so here's an example of Handle practicing some dance moves in our warehouse lab in our building. So I just love the fact that our warehouse robot here is doing some fancy dance moves in the context of a bunch of boxes and pallets. So it's really cool. So this is control work that was led by Shervin Talebi from the logistics group. And then, of course, Spot. Spot is a much more accessible and friendly robot. So most of the Spot control engineers were able to take a Spot robot home and work from home during last year. So here's some footage of dance preparation that was done by Eric Whitman in his basement. So we're getting weekly updates from Eric's basement, which is pretty cool. And of course, we're trying to plan this as a bunch of robots in the same frame doing something together. So we're trying to find ways to connect all these different threads of development into something that's a cohesive routine. So we have to get creative with things like video editing, where we're taking the latest and greatest that we have from our Atlas robots, combining that with the latest and greatest from Spot, making sure that everything makes sense together artistically, that the robots are keeping reasonable time with one another, and so on and so forth. So there's a lot of this kind of thing going on. And then additionally, one thing that was incredibly useful for us was to be able to leverage, again, our animator, Jakob, to create these animatics, which were a really careful representation of what the entire routine was going to look like. And so here, obviously, Atlas's routine was captured through animation. So we had a pretty clean representation of both Atlas routines. Spot and Handle are actually these rendering robot logs from the latest and greatest runs of their routines in this view. And we're having this top-down view here on the right that captures the actual geometry of our Atlas lab. And this was really helpful for us to be able to plan out camera paths that did the appropriate artistic reveals of one robot at a time, as well as making sure that the cameraman could actually move through the environment in a safe way with robots flying around and dancing and not crashing into walls or windows. So being able to do this level of detailed planning ahead of time before even putting all the robots in the same room was incredibly helpful and saved us a lot of time when we got down to the end. So eventually, starting in December, we started putting the robots actually in the same room together and trying to get as far as we could with the routine. There are actually a lot of changes that happened to all of the robots' routines in the last couple of weeks. So we felt like we got a lot better at being able to quickly adapt and change things and reorder things. So that was really helpful that that wasn't too painful for us. We were able to really nail down what we wanted at the very end. Here you can see Brian, one of our ops technicians, is playing cameraman for us and getting a real feeling for what this is going to look like on camera. And then eventually, we brought in a professional film crew, and this is the week before Christmas when we decided to film this. And once we had them there, we had to sort of teach them what we were thinking in terms of camera paths and so on. And in order to do that, rather than running the robots a bunch of times while they learned camera paths and tweak things and lighting and so on, we just had our engineers dance out the robot parts. And I think in an image, this to me is what it feels like to work at Boston Dynamics. It's a bunch of people who are extraordinarily bright and interested in having fun with the creative work that they're doing. They're all horrible at dance, but this is really just a fun time. And by the end of this project, we were really enjoying ourselves and really proud of what we're able to make the robots do. Filming basically extended over 2 days in the week before Christmas. Everything went really well. We had a lot of bonus footage, some of which was included at the end of the video. I didn't show that at the beginning of the talk today. This is one of my favorite outtakes where ballet quickly turned into karate. So we wrapped before Christmas, released a video right before the New Year's. And since then, Atlas has retired from dance. This was a really fun exploration for us to sort of exercise our model predictive control tools and optimization pipeline in the context of this sort of highly stylized motion. It was fun to see how far we could get with high energy full body dance. There has been one encore since then, and you might have seen this through Hyundai. There was a collaboration with the Korean pop group BTS, where the idea was to have Spot and Atlas both do a bit of a dance to a BTS song. And as part of that, we contributed just a single dance move as a bit of a cameo. And it was from this music video called Boy with Love. And so the question is, did we get any better at doing dance as part of this whole process? And I think the answer is yes. So, basically, we were able to take this concept video, throw it to our animator, and get back a first pass of the behavior. And then after 2 days, we had something that was polished and ready to ship, and we could put the robot in a production studio and film this sort of dance move. So this is good. It's also kind of not surprising. This is the kind of thing that this type of control system is really good at doing. But as a project, we're sort of not really working on dance anymore. We're on to bigger and more challenging and more exciting things that maybe we'll be able to come back and tell you about next year. With that said, Spot is still carrying the torch of dance at Boston Dynamics, and you might have seen some recent releases of Spot Dance, which are fantastic in my opinion. I get to say that because I didn't work on them. There's actually an ability for you or people who have Spot robots to interactively create your own dance routines. So there's a tool called Choreographer, and this is exactly the tool that was used to create the entire dance routine for the Do You Love Me video. And what's amazing here is that it's a nice interface that you can basically drag and drop reference motions that are really sparsely specified in terms of things like body translations, jumps, footstep sequences, arm motions, and so on. And these are interpreted by an online model predictive controller, very much similar to the one that we developed for Atlas, that is able to interpret and realize these behaviors on the robot in real time. So this is just an amazing way to interactively create expressive behavior on a robot like Spot, which is cool for people who are thinking about using robots like this for entertainment or for physical communication, things like that. Okay, I'll stop there, but I wanted to...
Yeah. So
That dance was really cool.
yeah. So this was all about dance that we had. Of course, there's in the parkour, I could find more information about parkour, and we covered that last time. And with the dance webinar, and I saw a few other resources. There's of course just the demonstration because it looks fun. But they do have these research papers and all linked in the webinar. So I'll share the link to the webinar and also the other resources that I found from last session. And if you want to explore more, I think that is a good way. So let's quickly talk about what we want to discuss in next week. So I think model predictive controller is at the core of all the things that they have done at Boston Dynamics. So for me, I think that makes sense. Has anyone of you worked with model predictive controller before?
No.
No, okay. But what do you think would be a good theme? The topic for next week. So the theme is still humanoid robots, right? So we have one more session left. We could take another robot or another, let's say, one specific aspect of it, or model predictive control, or what do you guys think?
I have a question. Did we do any kind of self preparation kind of a thing? Because what I'm thinking is, if we have gone through so much of uh, Atlas robot altogether, I have a suggestion. What do you think if we just think of a prototyping something of our own, just on paper, of course?
Like for example.
Just building something from the scratch and imagining just one action. It can be just running from one end to another.
Like we did with some of the other sessions where we defined a problem and then we
Yes,
brainstormed
yes,
it. Hmm.
yes.
Yeah, we can do that. But what do we want to cover in that specifically?
Good question. I think I don't have answer for
No,
that.
like just what we can also ask others, right? But what would be interesting for you, for example?
Um, I'm still more interested in the way how it's controlled without being or without throwing a path. What it's exactly doing. That means the control module, what you mentioned before, it's actually a good idea. The problem is that I don't know. I'm working on another project which we can. I'm still not a fan of. Let's say you give the robot exactly what he can do. For example, the stances move. It's amazing and how we are getting to this point, but still,
Mm-hmm.
um, I am more of the guy which is waiting for that the robot will have a reaction from outside events, which is and can behavior adjustively to what's happening.
Yeah, yeah.
And this
But it
is
is doing that actually. It is doing that. So we saw that it also takes inputs from perception. I think we covered this thing in more detail last time. But we you saw like for example, let me share the screen again. Of course, it's not totally of what you totally in that direction, but it. Let me open this slide from the previous one where they actually talk about how they want to progress with Boston Dynamics and what role perception plays there. Yes, here we go. This one. So you see here, the idea is so they have been focusing mostly on the core agility, and they have started to focus on the perception part, which we saw also. Um, let's say here, right, which we saw here, that they are taking the perception into account, but they are then adapting the trajectory that we got from the template behaviors, but that's still a very small aspect of it, right? It's not the environment is still structured, for example, for parkour and all. So but they're starting to do more perception in an autonomous way and interaction, but in the future they said that they would focus more on perception and are doing it in a more autonomous way, but they say that this is like one of their growth areas that they want to target in the future.
yeah, that would be the interesting part. I'm also interested in this new Tesla thingy, which is the robot. If they are also going to the perception autonomy, because most of the time, as you see, even here, it's the core agility is the most focus. I understand why they
Yeah,
get it working now, and after that would be the interesting part, how far they can push this interaction and the perception. If it's gonna, for example, something like artificial intelligence would be embedded inside, or even machine learning. This would be the interesting part, and how much it's gonna take and how it's gonna react.
yeah. Yeah, currently they're not using any machine learning at all, right? So that's the thing. But in the future, yeah, I'm also excited about what they would be bringing in, using AI, computer vision, and ML uh, to make this more autonomous in more unstructured conditions. So let's see how that comes about.
They are not using any sort of AI right now.
They're not using any. No, they are not using any. They're just using the only thing that I could find was this perception thing, but they're not using any machine learning or anything for that. But they're just taking the perception and then adapting it to the template of behavior. So yeah, no AI.
Oh wow! Oh
Yeah.
man. Actually, I so far
How it works.
till now I used to think that okay, it is having all this online learning kind of a thing going on. A very best example of
It's like
reinforcement learning.
no reinforcement learning at all. It's just pure control that they're like hardcore robotics and control that they're focusing on.
Uh-huh. Okay.
Yeah, which is also challenging, but now yeah, would be interesting to see how I mean, the thing with deep learning is that it's not really as reliable, right? And for
Yeah.
these complicated motions, yeah, would be interesting. I mean, of course, there's research in using deep learning for allowing the humanoid robot to walk and do simpler actions, but these are like more complicated things that they're targeting. But let's see how they do it. Reinforcement learning would be interesting to see if it is possible in a certain extent.
Yes, that's true.
Yeah. Okay, so yeah, just let's quickly conclude about next time. So thing is we can do uh, how model predictive control. We can just talk about theory of model predictive control. This is one option. Another option is we can take up, let's say, a walking problem, how humanoid walks, and we can then do brainstorming and discussion. And I don't know, they probably also use model predictive control or something, but yeah, we need to search that up. This is another option. And the third option is we take another product, let's say, which one, like Azimo by Honda, or yeah, or any other humanoid robot basically. So these are three options. What just let's have a quick voting and we can just finalize it immediately.
How about my vote goes to the second option, finding the how it will work, brainstorming on that.
Okay. Okay. Yeah, so yeah, humanoid walking, and we can then discuss in details. And there's a good chance that the model predictive control would be used there. But
Yeah.
yeah, so that's I think a good suggestion. And Jidnyasa, what do you think? Okay, then Juan Diego, can you hear us?
Yeah, I think I prefer more the first option. I would like to know more about this kind of control.
Model predictive control, more theory. Okay.
Yeah.
Yeah, Krish, I don't know if you joined the whole session yet, but I think you get the question.
What was the question again? I was busy.
Yeah, so basically, we are taking a voting on what we want to discuss next time. One would be model predictive control, just theory about that, and other would be taking a case study of humanoid walking and then brainstorming and coming up with a solution of that. And the third would be another, let's say, another product or another robot, another humanoid robot.
I think case study would be better.
Okay, okay. And Lucas?
I would go with the first option actually.
Okay.
But we can also join with the second one, the brainstorming. It's both of them are interesting, but the first one with the adaptive control module, it's
Yeah.
also something because I'm interested in.
Actually, I think the two things. If the humanoid robot walking, if we take up a problem where the humanoid walking can be done using model predictive control, then we cover both
Yeah.
of the things, right? So it does make sense. Omnidirectional humanoid walking. Yeah, I guess we can find some paper. Omnidirectional humanoid walking using model predictive control. So, of course, this was a very quick Google
No,
search,
I
but
think
we definitely would
so.
find
If
something.
we, I just have a question that so
Yeah.
if we go through this model predictive control, will we be able to understand altogether the motion of robots? Is that so?
What do you mean overall motion of robot?
Like say walking, running, jumping, things like that.
I'm not sure. I think we will get a really good idea if we understand walking. Then we can link it to what we saw with the dance and the parkour movement, and I think we will definitely have a good understanding.
So if we do model predictive control, then we can actually also cover walking in the later stage, right?
If we take the first option, you mean?
Yes, yes, yes.
Yeah, I think so. I think so. But I guess like so the idea with if we take just model predictive control, it would be like a general overview. We would not be probably discussing about humanoid walking. If we take humanoid walking, our focus would be on humanoid walking. But how model predictive control applies to that, So I think it makes sense if we take a combination of these two things, right? So
Yes.
so we see how it is being done also. So here, there is a bunch of resources. Model predictive control for biped walking. Not sure how easy it would be to understand though, but let's go with it. We'll figure something out. Yeah, at least we'll understand something, right? So MPC for humanoid gait generation. Yeah, let's go with it. Let's go with it.
Um, I I cannot promise, but if you share through this week what you actually come to, I can maybe help in the presentation. But I cannot promise. It depends on if I get the time.
Okay, okay. Yeah, or I mean, do you know something about this MPC, or have you worked with it?
I did in my first master, let's say a bit about it. We built a robot also but it was in first stages. So I had or I have some ideas which I can present, but yet I need
Yeah.
to refresh my memory for a lot of stuff. So for that, I cannot
Uh,
promise if I can do that, but I will try my best.
okay, I think that would be pretty great. But even if you just join, I think since you have worked on it, you would be able to remember and recall stuff, and I think it would still be very helpful.
Yeah.
Even if you
All right.
like can't prepare, just if you simply join, I think that would be helpful enough, I guess.
Sure, sure. Of course.
Uh, Chandandeep, in chat room, I have shared one link on MPC. If someone's this is there.
Okay, it's a PDF.
It's good slide actually. I'm just going through and thought it's good.
Okay. Okay, perfect. Yeah, I think we can check out this as well. Yeah, looks very compact. So yeah. Thanks for sharing. And yeah, so before we now wind off for today, so there's another presentation that I'm giving on the AlphaBot robotics community. For those of you who joined, the guy Akshay Nambiar also presented his about his server there. So if you have time, you can join it 1 hour after this. So that would be 5:30 p.m. IST and 1 p.m. CET. I'll of course add it in the announcements as well. So the what will be covered is basically how to start learning computer vision now. uh, yeah, so how to start learning computer vision, and I'll be giving an idea of how you can begin learning computer vision from scratch for beginners basically, and giving sort of a roadmap. Let's see how that works, and it would be also a more interactive sort of a discussion, but I'll add it in the announcements, and so if you want, you can join. And that's it. So before the next session, I need some time to actually, make the PPT a bit better and also relax a bit. So we can wind off today, and next time we can talk about humanoid walking using model predictive control. All right. Thanks a lot, guys,
Thank you.
for joining today's session.
Cheers.
Bye.
See you later.
Bye, guys.
Bye.
Bye, guys.